My name is Tom Purcell. I'm a consultant with Chariot Solutions. Uh, Today's talk is being given by Todd Montgomery. Um, Todd is an independent consultant and a committer on Argana, Arion, RSocket, and Fix SBE. Todd's talk today is called Modern Inefficiencies, Performance on Modern Hardware. From his abstract, it looks like he's going to tell us how not to get burnt when they hand us a new set of fancy matches. Todd, take it over.
Thank you very much. And thank you for having me today. I talk a lot about modern hardware, and I really do come from a background of protocol development and networks and performance. But I do want to talk, today about, a little bit of journey that I've taken, and kind of sprinkle through trying to sort of explain how my view on things has changed over the years as well. So a little bit more about me. I, I deal a lot with performance and network related protocol development and things like that, mostly in the financial sector. I work a lot with traders and exchanges and things like that. And I'm a consultant and do that. I also work in open source software, but traditionally I actually started by working for NASA on software safety and software quality. So I do have a look, I look an awful lot at things that are performance related, and I look at it as more efficiency than just simply speed, and also as quality. And we'll kind of get into where I think a lot of those things fit. So the talk today will really start by looking at why we should care about efficiency in computing and performance and efficiency specifically. We'll talk about modern hardware and some of the system software that we have, and some of the other pieces of software that we usually consider to be lower level. And we'll talk a lot about understanding the inefficiencies that we tend to do. And I'll phrase this by saying this is the trajectory I have taken over a number of years. And I'll go through the things that I think I've learned and try to give you a sense of it. So why should we care? This happens a lot when I give a lot of and discuss performance and efficiency. Is what is it about performance and why should we care? And I do want to kind of talk a little bit about the fact that data center electricity usage, but not just data centers, it's also communications, wireless and wired, infrastructure, televisions, computers, mobile phones, everything. Our projections, and this is from a few years ago, but our projections are still pretty much the same, is this will take up a vast majority of things eventually in terms of our energy consumption, but it grows very quickly. If you look at it just now, we're about 1% of total energy consumption, but predictions of this go anywhere from 8% to 21% in the next 10 years. And this is important because one way we can reduce our footprint is to be more efficient with all of our resources, not just consumption. So efficiency and performance is really what we want to talk a little bit about here, being efficient. And this is, we normally think of performance or these as one of those non-functional requirements. And I prefer Martin Fowler's term cross-functional than non-functional. And it really does cut across. Usually it goes without saying, that you want something to be performant enough to meet whatever characteristics it is. But at best, this type of performance or quality or security or everything is at best afterthoughts. And that's sadly, where things come down. And I don't think that's bad. I think a lot of times we think of it as an afterthought, but that doesn't mean that it isn't something that we have to eventually consider. And often what this means is that a lot of these abilities, it isn't an issue until it suddenly is. And then how do we deal with it? And a lot of the times when I work with, a lot of different teams, I'll hear things like, but it doesn't have to be fast, or that's not MVP. You would think that's kind of odd coming to the fact that most of the time I'm the teams that I deal with and have dealt with over my career have usually, been looking at performance. But a lot of times, little pieces of a subsystem doesn't have to be fast, but it doesn't actually have to be slow either. So we should think of it a little bit more as fast enough to meet those cross-functional requirements. But a lot of times we seem to assume that these other things are characteristics that are added separately and or later. And I wanted to kind of challenge that because most often it's not. And so to sort of give an example of that, in the age of cloud, a lot of times when we want to do scalability, we just throw machines at it. And this might reach the goals that we have. It may be inefficient, but it might reach it. So if we don't think of it as an afterthought, how should we look at it? What should we do? And for me, it's taken a number of years to kind of really get the idea of where to focus effort. And this is something that it took many years of kind of understanding to think of it as the Pareto principle or the 80-20 rule or a power law, in that 80% of your whatever you're looking at, by concentrating on that part, you have much more impact than if you look at the 20%. And one of the reasons that I think this works really well is that if you take this from the planning idea or the design aspect, the planning is important. So if you realize that a critical piece of a system, something that has to work well, or it has to be secure, or it has to be high quality, and spending your time there on the design pays off a lot more. And, the thing we do specifically with efficiency is first we take a guess of where we're going to be inefficient or where there's going to be challenges to making something efficient. And we tend to spend our time there when we have developed that sense of where to spend it. And that's what I want to try to get across, is where you might think about spending your time and developing that. Later, though, it's just as important to take measurements and guide where you should look after that, because your initial guess is going to be off. But it doesn't have to be perfect. You take an initial guess based on experience, you take an initial guess based on the characteristics that you want, and then letting something like a more of a scientific method, measuring, guide where you should look. And this is really that famous quote about premature optimization kind of comes from. The quote is really not that you shouldn't optimize early, it's that you should know where to optimize based on evidence and based on knowing how to measure and how to look at something, and not looking at that 20%, look at the 80%. So developing a sense of where, I think, is important. And that really, it comes down to, in one sense, our modern hardware. So understanding our modern hardware goes to not just CPUs, it goes to IO, it goes to various other systems. And it isn't just all hardware systems, in other words, physical things. It's also virtual things. It's also software. So in fact, most of our hardware is actually software. There is a lot of the things that are done on chip are actually software in nature more than they are hardware. Let's take a look at that. So most modern CPUs have, if you remember some history, we have kind of increased the speed and the megahertz of CPUs, but that's kind of plateaued. We've added cores, but I won't say plateauing, it's slowed down dramatically. But things that we've seen are not just more cores. We've seen an increase in speculative execution. What this means is that taking your previous history of how you have processed things and making guesses, because that's what the processor does when it's doing speculation. It takes guesses about what you're going to do and tries to do them before you do them, actually. And this has led to, in one case with Intel, leaking of information via Spectre and Meltdown. It's that taking bets where we have seen that be very popular. But it's not just that. We have things like lock elision, which is a technique of transactional memory to elide the cost of locks. We have caching and memory buffers in the designs of our chips that mean that basically when you write a variable or you write a piece of data, that you're not actually going and physically writing it before you return, that you're actually pipelining a lot of that. You're doing the chip's doing very complicated things underneath the covers to give you an illusion of speed, even with even slower pieces of memory. Single instruction, multiple data. SIMD instructions are a great way of speeding things up. These are inherently very parallel, and they are extremely efficient. Specialized processors, we're doing machine learning, or our GPUs are specialized processors that not just when they're on chip. But a lot of the times what we have is a CPU that is a communication bus. A lot of these components talk to one another via this bus. Your cache is setting on a communication bus and using a protocol to talk to other caches that are for other cores. So, these, from the CPUs, we have grown to have sort of a trajectory where there is very specialized hardware for even things like secure enclave for various types of chips. And our memory models for CPUs have grown in that sort of way. And that leads me into Intel has risen to be a dominant player in where our chips have gone. And they pretty much dictated it for a long time. But we've seen that start to fall now. We in ARM and other as well as other areas, we have seen where different approaches, and we've sort of seen this over the years, the CISC versus RISC. If you're sort of a white bearded guy like me, you remember these days. But the rise of Intel and the rise of speculation are very inherently tied together. Dominance as well, and now we're seeing sort of the fall. So Intel has had a very important impact, but it's not just Intel, because when we look at like the architectures of things like ARM and other types of processors, we definitely see a trajectory. That trajectory is also kind of mirrored in how we look at a lot of I/O as well. So you'll notice here that I'm not talking about anything very specific in terms of I/O, aside from SSDs, Optane drives, things like that. Kernel bypass with something like SolarFlare, EFVI. These are specialized hardware, but there is a lot of software systems that enable and allow access to some of the better characteristics. DPDK and SPDK. DPDK is basically a means of getting at very low level aspects of a network card. SPDK is the same thing, but applied to storage. These development kits are available across different NICs, across different OSs to a small degree, but mostly Linux-based. And you're looking at enabling different things within the hardware. OU ring is a totally software side effect of this, and trying to provide a async kind of interface on top of inherently things which are synchronous by design from an API perspective. So with modern I/O, you're looking at throughput versus latency. These are not trade-offs. You can have high throughput and low latency, but it's awfully hard, to look at something like latency and throughput separately. They do have some relationship to one another, but they're not dependent on one another, if that makes some sense. But if you look at both CPUs and I/O, the commonality that you'll see is that inherently these are highly parallel. Now, when I say parallel, it is literally that other things are happening while you're doing something. In between two different instructions on a chip, very seldom is it just waiting for you to complete. There are all kinds of things which are going on. The same with I/O. Just because you wrote a piece of data to a drive doesn't mean that it immediately makes it onto the stable storage. It's going to go through various levels of caches, which mean that those caches flush asynchronously. These are inherently asynchronous by design, because that's how they become faster. They're high throughput. I/O and as well as these chips. Between the core processor units within most Intel chips, you're looking at a very high speed bus Even your moderately what I am using on this somewhat older MacBook Pro that I'm presenting to you on, it has 9 gigabits per second between the cores. So you have high throughput at your fingertips. But if you look at traditionally the latency that has been going, that is on these systems, it has not grown, it has not shrunk much. It's nearly constant. So when you look at the latency that is there on most hardware, you're not going to beat the speed of light. I'm sorry, it's just not going to happen. Right now, at least as far as we know. So you are limited in terms of what the latency is. So that's a characteristic that you're going to be limited on. So I want to that sort of sets the stage. We have an asynchronous, highly parallel hardware, whether it be I/O or our CPUs. They have high throughput, and they have nearly the same latency. Latency matters much less, and we don't have that as something that we can lean on too much. We normally think of our tools when we're as software professionals as being languages and runtimes. In fact, we have arguments about what is the better language all the time, right? We think of these as our tools, but I want to challenge that because I think this quote from Steve Jobs is very apropos. When you want to do something well, when you want to be efficient, when you want to increase the quality of what you're looking at, a lot of times you have to look at your ingredients, your components, your materials. And I think we a lot of times don't do that in software. We let that be an afterthought. So I would challenge that our tools are not just our languages and runtimes. In fact, they're a small part of that. It matters a lot. Our CPUs, our drives, and our NICs, et cetera. And it matters even more when we're in the cloud, not less. Just because we have virtualized hardware, to sort of say, doesn't mean that we shouldn't be concerned about it, or we shouldn't be aware of it. Our hypervisor adds an additional dimension. It doesn't hide or abstract it away. So when we want to think about this, and we want to consider that our CPUs, our drives, and our NICs are effectively our ingredients if we're a chef, right? And we think about, to do this well, we need to be aware of our ingredients, pick them well. They have a lot of the same characteristics, whether you pick one or another, just like a lot of other ingredients, right? Or another components or materials that we're interacting with. So if we know that it's highly asynchronous and it's highly parallel, has high throughput, but latency is there's very little difference. We then have to think about, why do a lot of times things get inefficient? And I'll take you on a personal journey over, decades, really. I saw this pattern a lot while dealing with systems that the system was slow. One of the first attempts is you throw hardware at it. Now, this used to work a little bit better when we were kept increasing megahertz. You could throw faster hardware at it. The system would get faster. Sometimes it is still slow, a little bit better, but not really better, right? Well, over the years, I've found this sequence, kind of led into, understanding a lot of the inefficiencies that we do. And the modern inefficiencies we do is a direct result of the fact that we had this cognitive dissonance between, what the hardware has tended to grow in a certain trajectory and our perception of how we have designed systems. And I break it down into 4 different things here. And there's going to be a 5th one that sort of wraps it up because I think it's an overarching thing, is premature waiting. And we'll go into these things. Premature waiting is going to be one of the things that I saw many times. It didn't, a lot of the times, the cure for that tended to go into wasting resources, which then to sort of alleviate that goes into not understanding why doing a solution, and then eventually coming into us not enabling the good things which are in our hardware and some of our software systems. So to go into these, and I understand these may seem weird at first, but let me take you on this journey. So the first, premature waiting. I think you should realize is that ordering is an illusion. Our compilers can reorder. Our runtimes can reorder, our CPUs can reorder, and they do this to be efficient. They do this to, at the CPU level, think of it this way. If you're writing two variables and they're in different registers, does it matter, and they don't depend on one another, does it matter the order that you write them, the CPU? No, it does not. Does it matter when you're writing them to two different areas of memory, and they don't depend on one another? No, it does not. So the CPU can try to do things that are more efficient, but so can a runtime. Thinking here about a Java or C# runtime, or even some of the, as things have sort of progressed a little bit into more of a C++ runtime and other languages. And compilers. Compilers can look at this and say that there's no dependencies between these two different things and can order them based on whatever can lead to a better, and more optimized solution. But that doesn't mean that anything can be reordered, right? We do have this illusion of sequentiality, because what we have done is the compilers, the runtimes, and everything else can order and provide and impose an order if they do depend. So we have this illusion of sequentiality, but it's not just compilers and runtimes and CPUs. We also have this with various aspects of these entities too. So load store buffers in CPUs are definitely used, to provide this illusion. In fact, the way that Intel does this and other manufacturers of CPUs is to snoop on the store buffers, for example, to not just have to wait till something makes it to main memory, but to snoop on it that it's going to be written to main memory and to understand what it can do. In fact, this is where a lot of the complexity of these things comes into play, in that you try to provide this illusion of sequentiality. So no matter if you're using an ARM processor or you're using an Intel or you're using something else for an embedded space, you always have a memory model. And that memory model is your illusion of sequentiality. But storage and caches also have it. The virtual memory subsystem and caches within an operating system also have this illusion of sequentiality. They provide this illusion so that there's things that you can hang your hat on and know things like linearizability of writing something and be able to read it, these things like that. But this also even allows to even think about things like specialized processors, like security, like secure enclaves, machine learning, GPUs. All these have also some memory model and illusion of this sequentiality. Now, just because it's an illusion doesn't mean that it's not valuable. In fact, it's tremendously valuable, to have this illusion. It is fundamental. Without it, we could not function. And we have it also in the software version as well, with libraries like promises and futures. Promises and futures allow us to sort of go off and do other things while we might want to be waiting for example, an answer to a request. Now, we'll get into this just in a second, but it does allow us to do that. When we take a look at even something more different, networks themselves have also an illusion of sequentiality. In fact, most protocols reorder messages. They get rid of duplicates. They get rid of they send retransmissions for loss. This is a space I've lived in for a very long time. But even between, and just you may think, well, I'm using TCP with a REST endpoint. What does this matter? To me. But if you think about it, even between TCP session getting disconnected and reconnecting, what has happened previous? When did it disconnect? How? What has happened since that? These all things happen not just at the individual transport level, but they happen in a sort of a system or session level as well. And these things have throughput characteristics as well as latency characteristics. And to sort of give you an idea of what premature waiting is talking about, is it's synchronous. So when you wait, when you send a request and a response, I'm just using this as an example. This can also be initiating an action that is asynchronously done by the hardware underneath. When you send a request and something else is done and you wait for a response, that's latency bounded. You're bound by latency. If you cannot do anything else after sending that request until you get that response, you are bounded by latency. That's waiting. But if you can do multiple things, initiate them, and then have responses come back asynchronously, now you're throughput bounded, okay? Now you unlock yourself from the sort of tyranny of the speed of light, and now you can, go at the speed, that throughput, and how our chips have sort of grown, looking at throughput as a function that increases. So that's what I talk about premature waiting. A lot of times we don't spend enough time looking at the fact that we have initiated something and we have to wait for a response. There's so many things which are inherently async that we should think a little bit more. And to be quite clear, I think sort of a multiple requests and multiple responses, that model, that event-driven model, is a much more effective way to think about systems. And I also think they're simpler. But so a lot of times in my own journey, it's the freeing of the synchronous activity, that is the first step. It's the unlocking. And the way that our hardware has grown, it's important to take that step, to understand that you're being inefficient when you're waiting. So thinking about what can you do while waiting. Our initial reaction to this a lot of times is to, quite frankly, we throw cores at it. We think, well, I don't know exactly what I want to do, so I'm going to let the operating system pick it. And so we end up a lot of times with that wasting resources. So to sort of make this concrete, when your number of threads exceeds your number of cores, you're going to probably be inefficient. You're going to probably be wasting resources. And this is, again, normal reaction to something like you understand that you're waiting a lot, and all processors wait at exactly the same speed. Doesn't matter how fast they are, you're still waiting and not doing anything. Throwing threads at a problem more than the number of cores leads you to its own issues. And it doesn't really matter if they're IO heavy, although it matters a little less, but it still matters, or they're CPU heavy. In other words, are those threads hogging the CPU, or are they mostly just waiting around for IO, or are they just waiting, period? It does matter, but it matters a lot more about what underneath is going on. The locks, the caches, the way that IO is being treated. And it really boils down to is when you have more threads than cores, you're contending. You are introducing contention. You're also introducing something that's even worse, which is coherence, the coherence penalty that is attached to it. And to sort of give you sort of an example of this, I'll show you Amdahl's law and universal scalability law. The blue line is Amdahl's law. And Amdahl basically wanted to show that multiprocessing wasn't all green field, right? It wasn't all just roses and daisies. That it came with its own complexity, and it had to be managed. It had to be handled in some way. And so he came up with a very interesting equation. And it basically means the speed up you get by adding more processors is a function of how much of the workload is totally parallelizable and how much of it is serialized. In other words, you can parallelize some of it, but there's going to be an inherent piece that is serialized. In other words, there's going to be a lot of waiting that has to do at some point. And that blue line, see it asymptotically goes to 20? That's because 5% of that workload in this graph is serializable. So 95% parallelizable, 5% serializable. The max speed up you'll get is 20, no matter how many processors you start throwing at it. That's what Amdahl's law states. But Neil Gunther came along and he said, you know what? I think that this ignores the coherence penalty of having all those processors share their state. In fact, I think it's worse than that. And he came up with something called universal scalability law that kind of shows that it doesn't just asymptotically go, that it gets worse, that there's a sweet spot of number of processors based on the coherence penalty. And that red line is that penalty. And that's 250 nanoseconds of coherence penalty. This is based on just the cache traffic that is being used between processors. In fact, and if you've ever run into this, you have a job that's parallelizable, has a little bit of serialization in it, but you're reasonably confident it should speed up, but you throw things at it. You notice that as you throw more at it, it gets slower. This is what you came into. You came into the wrong side of the universal scalability law, and you're trying to get out of it. And this is why having basically something which is inherently looking at more threads than cores can often lead into exactly this. But does that mean you're limited? No, it doesn't mean that you're limited. It just means that thinking about what your threads are doing matters a lot. In fact, it matters a great amount. Normally, you, and this is my trajectory, throwing some threads at it, being careful about what they do, so not kind of coming into introducing a huge amount of coherence penalty, and then not seeing the speed up that you wanted. I can exactly determine that, what I did was to, in essence, then say, well, the scheduler must not be very good. I know what I'm doing. So I'm going to pin these threads. And this is where not understanding the why. When you start to set a thread affinity, and now you're saying, I want this core to run this thread, or this thread to run on this core, and to do this, the understanding of why doing that is subtle. In fact, it may seem like a great idea to reach for to do this. Just pin the thread. And understanding the why is important here, and I'll explain why. But we see this in all kinds of other realms as well too. Microservices, machine learning, AI, blockchain, you name a technology, not quite understanding why and asking the question of why, what does it do, what does it actually do, and understanding that fully can sometimes lead to inefficiencies. And I'll give you an example with thread pinning. Why you pin a thread is to reduce cache traffic, also to reduce the number of context switches that an individual core does, therefore changing the cache invalidation that happens on the system, and optimizing the data flow to and from I/O. What this means is that if you don't understand your data flow, and you don't not just pin, but keep other things from running on that CPU, you don't help yourself. You make it worse, because you're saying, I know better than a scheduler what is going on here. Most of the time you don't. The scheduler is pretty darn sophisticated. It knows a little bit better. It can move things around. It can learn what is a better way of doing things. So saying that you know more than the scheduler, that's a tough thing. And if you do happen to know these things, then thread pinning is a great idea. If you don't, then thread pinning is a bad idea. And in my case, for the example I'm sort of leading you through, I found that if I didn't pin, things were much better. Why is it when I pin that they're worse? And my actual problem was that I think about was I didn't really realize the data flow. And to give an idea about this, the network, reading a packet from the network, where that data goes, where that data is shared in cache, all those things matter. So once I understood that, I was like, oh, I do know better than the scheduler. I can say it comes into this on this machine, it comes into this package on this core, it then can go to this other place and be shared here. When I was able to set that up correctly, now thread pinning was helpful. But before that, it's not. So understanding the why, there's a subtlety there, is important. And notice this also it comes right back to universal scalability law, because I was running up against that exactly at that point. But there is the first level of things that we've sort of mentioned already in this little journey, is really about disabling what so many systems are trying to do for us and not enabling them. And to sort of step back for a moment, hardware, compilers, the operating system, runtimes, all these things rescue us. They have so many different pieces to them that are efficient. Caches, schedulers, the out of order execution on the chip, lock elision, garbage collection, the speculative nature of not just execution, but speculation based on caches and striding and everything else. And the optimizations that come about, whether it be profile guided, like you would have in a JIT, like say Java, or it's ahead of time, like you would have in some native languages, C, C++, everything. These are great. They can take a lot of our mental model and do things that we could never have foreseen. In fact, that's the challenge. But we so often defeat these optimizations when we try to be too clever or let our complexity grow. Um, what we need to do is enable, not disable. And what we tend to do is to disable and not enable. And to sort of give some examples, garbage collection and object ownership. I've seen this with Java. I'm going to pick on Java just a little bit, not because I don't like it, because, well, I deal with it a lot, and I hate all languages equally. But a lot of the designs also with Java tend to be very garbagey. And the object ownership in a lot of systems is very doesn't normally reflect our model mentally. We a lot of times just let garbage collection deal with things, and one of the things we let them deal with is object ownership a lot of times, and it tends to be very disruptive and not be very clean about who owns an object, when is it supposed to be cleaned up, how is it handled, and that often sometimes leads to odd things. I deal a lot with native languages, especially C, and I have spent actually over the years more time actually looking at memory leaks in Java with than I have in C and C++, because object ownership can get very tangled, because it's not a first class concern. It's something that you let the operating system do. But here's where the enabling gets by having unclear object ownership, you end up with garbage collection a lot of times being heavier weight than it needs to be. And this is subtle. A lot of times we think about dealing with garbage collection after we've realized that it's a problem. But whereas when you tend to think about object ownership and the coherence between objects, which is different than cache coherence and things like that, and thinking of it much more in terms of how can I make it so that it's very clear my mental model about how objects are owned and how they're shared and the coupling and coherence between them. I've noticed that whether it's a bias or not, I don't know, but I've noticed that garbage collection tends to only come into play, as a bad thing when that is not clear. So one of the things I often do is when I notice the garbage collection is taking a long time or it's becoming a problem, is to look at object ownership. It's because we tend to, when something is done for us, we tend to not think about it. I think that's totally natural, and it probably leads to great designs, but it also means that the downside of it is because it's not top of mind, you can get you get away with a lot of bad behavior, and object ownership seems to be one of them. Escape analysis is something that I'm going to say I'm not a fan of in various languages. And escape analysis, really what it does is you're looking at trying to see about a temporary object and seeing if it escapes a certain scope. And if it doesn't, you can optimize it by not being heavyweight with it. Again, I'll pick on Java just for a second, in that you do new on an object, and the runtime can determine that it doesn't escape this context. So instead of creating a new an actual object and allocating it, it actually uses just registers to kind of hold its state, and then it will just happily let those be reused. That's escape analysis. The problem with escape analysis all too often is that it very seldom spends a lot of time trying to figure out if something it has escaped or not. And its criteria is incredibly precise. Almost all languages that have escape analysis, if you start to look at them very heavily, you'll see that most objects escape. Not that actually they do escape, it's just that the runtime assumes that they do, because they can't see far enough, or that the criteria that they use is very, very tight, and it only fits a very small selection. And so it's very hard to lean on escape analysis very heavily, as something you can rely on, that it will automatically be faster. You have to really fight to make escape analysis efficient. And so, but I think that there are ways of doing that. On the CPU side, I'll pick on Intel just for a second, but it's really difficult with the way that ALUs work for a lot of the older Intel and some of the newer ones, when you have division, because a division operation is expensive. It will do a lot of things that are fairly destructive to performance. Not intentionally, it's just an expensive operation, even in hardware. And so this is really tough because we don't normally think of it as a software, designing software, that division is something which can affect our performance. But let me tell you, it can. Once you get to a certain level of caring about it. But it's is there a way that you can reduce it? And to sort of look at this, since I've dealt with a lot of business logic in trading and financial institutions, and looking at financial equations, a lot of times looking at simplifying an equation is can I get rid of some of the more costly things that this is doing? Can I simplify it? And we'll come back to that word, simplification. Can I simplify it so that the penalty that is associated with that, it can be lessened or it can be controlled in some way? And that leads into sort of, when looking at this, simple versus complicated. You'll notice when I talked about it is not defeat these optimizations or these things that are great, by being too complex. And that's really where it comes down to, is you want things to be simple. You don't want them to be complicated, and it's deceptive. And the best thing I can think of is, if I've over the years, one thing I've learned is that I am more stupid as I learn. And the more things that I have realized, the more I've realized the things I don't know. And so to look at something and to fully understand it, it has to be simple, at least for me. So how could a software system like a virtual memory subsystem, how can it, really understand what is going on if I'm too complicated? If I can't understand it, if I can't fully sort of hold it mentally in my head, how can another subsystem, whether it be a CPU or the operating system, virtual memory, or the file cache, or a cache subsystem on a chip, how can it kind of understand it if I can't? Same for a compiler. How can you optimize something when the compiler can't even look at it and go, okay, this is being touched and this is being touched, and this is come back to escape analysis. This is also that part too. How can often why escape analysis is defeated, is because of too much complexity. So if I had to say that, one additional inefficiency we have is we undervalue that power of simplicity. And that comes into what I think our modern efficiencies are. I think simple composes more easily. When we relentlessly spend our time, that 80% of our time, looking at something and trying to simplify it so that our mental model is easier, so that our debugging is easier, so that everything is, we enable all these systems. Simple often optimizes well. This is something that took me many years to really kind of get in my head, but it does over time and time again. When simplifying, things optimize better. So simple can be fast. It can lead to being efficient. When you have that ability to look at it and say mentally, I can hold that model in my head, you've now enabled the system to see all kinds of interactions that you didn't know about and to optimize those. So that leads us into sort of takeaways from this. So the goals that I wanted to do here is I wanted to talk about ways that we are inefficient. I want to use this kind of a journey that I went through over many years, and think was very valuable to me as a way of sort of pointing out some of the inefficiencies we do and how it kind of deviates from what the hardware is doing. But I also want to stress that simplicity is extremely valuable. It enables a lot of the good things that we get. But none of this is specific to modern hardware. I think it's just more pronounced. And to sort of, go back, the question we often ask is, we have a slow system, we run it on something new, a CPU, a NIC, or a drive, and you thought it was going to be fast. And it turns out it's still slow. that's that key. Spending the time of really starting to look at, okay, where is the inefficiency coming from? Where is it because you're waiting when you shouldn't be? Is it because you've got a lot of threads going on and potentially there's contention and coherence? Is not understanding why certain things are done, not just the thread pinning. Although these are all examples, but understanding the why of something and where it shines and where it doesn't shine, and understanding what that is and what has been disabled instead of being enabled. What inefficiency has crept in because not making things as sort of clean as they could be. That's the things I'd like you to take away. So with that, I'll turn it over to some questions.
Yes, Todd will be taking questions in the Slack channel for room A, if anybody's interested.
So the question is, you said you hate all languages. Care to go into more detail? Yeah, actually, I could. So I think familiarity does breed contempt. I'm very familiar with C, C++, and Java, and I hate them all equally, but for different reasons. Java, uh, I don't like the syntax very well, but that's a minor thing. Syntax, I think, is a poor reason to hate a language. I think that some of the ways that Java has progressed um, is has been detrimental. And first is I love the idea of garbage collection. The actual reality of garbage collection in a lot of systems is a different story, and that's why I picked on it. In C, one of the things I love about C is I don't have to think. I know that there are only a couple ways to solve certain problems, and I just get on with it. So that's the thing I like about C. The thing I don't like about C is that is only a few ways to do it, and I have to get on with it. I'd love to have a little bit more ease of doing certain things that I like to do in C. In C++, it's the opposite. There's way too many things to do. And so it's hard to pick the right thing to do in certain situations. Java has the same problem. So that's kind of, at least some details. If you want to know specifics about other types of languages, there's other things. I think, one of the things that I just mentioned about C++ also affects things like Scala. Um, One of the languages I do like a lot, and I wish was faster, because I deal a lot with efficiency and speed, is Erlang. I like some of the concepts of Erlang. I like the model of Erlang. I just wish it was a little bit more performant. That's probably the one that I deal with on a recurring basis that I wish was a little bit more efficient. Yeah, so that's kind of where I would go with languages in a little bit more detail. You got to be careful though. This is something that you ask anyone who deals with a lot of languages on a very regular basis, they'll go into them for quite some time. In another question, I'd like to know more about object ownership patterns for better managing it. Actually, I think that that C++11 introduction of shared pointer, unique pointer, and weak pointer was a great addition, but not because of them directly. I think the result of having to think about something be either unique, in other words, there's one owner, or multiple owners shared, or having a weak pointer, which could be invalidated at any time. That model, that sort of three different things, and that's it. And having it sort of pervade through libraries and things like that was a good simplification, because it definitely, by sort of contracting down gives a much better way to think about ownership, and not just ownership of objects. I think ownership of resources. And I think that that can be, for a lot of systems, a better way to think about it. In terms of other patterns, actually, I go back to some of the early patterns, like singleton, and I know people are going to jump on, me for that, but I think singleton versus, not a singleton is one aspect to think about. Um, I think, but I think more than anything else, when you start to look at, shared versus unique, that's a real key for me, in terms of object ownership, because there's a penalty to be paid when an object has multiple owners, or a resource has multiple owners. And so that, is a big step. And having something which is weak, where, you can have that. I think that actually that sort of triple is a decent place to start. Um, I don't necessarily prescribe that that's all that there is, because there's way too many subtleties to all of those. But I do think that it's worthwhile when you start to look at object ownership, as opposed to just saying, oh, there's a pointer to it. And so, yeah, it'll go away eventually. I think making those things clear. I know that others have a lot more breadth in terms of coupling and coherence and everything else between, with objects specifically.
You go.
I related a lot to your talks regarding threads versus CPUs to scaling up approach to putting resources on a job. Do you think scaling out can help in speeding up processes? It can. So one thing I should have mentioned is that I don't believe in absolutes. So I try to steer clear from saying you should always do X or you should always do Y. One of the things that when thinking about how to sort of phrase the things I wanted to say, is that example of just throwing machines at a problem to scale. Sometimes that is the right thing to do. It can be very beneficial. It can also be detrimental. Some of the same things that throwing machines at a problem can show is like also throwing threads at a problem, right? A lot of those things can show. Protocols specifically have potentially a lot of premature waiting in them. You send a request, you have to wait for a response before you can take the next step. So that adds round trip time into a sequence of events in a system. And so trying to deal with that can slow things down. I've seen instances where, just throwing another machine at a problem was definitely the right thing to do. And I've also seen where throwing another machine or another core or another thread at a problem was exactly the wrong thing to do. So I think that there is, definite areas where these things can go, but it comes down to the why, right? In terms of if there is inherently some aspect that is parallelizable, and where there's no dependency, then that's where you want to put something like, speeding up. You can get speed up because you're reducing in that. And even if there is some small bit of serialization, if you can minimize it, or even if you just say, hey, it's 5%, you go into it knowing that you have limitations like Amdahl's law. Or that you kind of can get to a point where even that 5% is worth it. Going in with your eyes open, understanding, at a deeper level, I think is tremendously valuable. And to sort of also talk a little bit about USL, Universal Scalability Law. In computing, in software, we don't have the equivalent of what I'm actually an electrical engineer. My degrees are in electrical engineering, and I come at software as an electrical engineer. It's kind of weird, but a lot of the underpinnings of my engineering discipline that I learned was driven by Maxwell's equations. which effectively is just saying how electricity works, and how electromagnetism works, and how field theory, and everything. We don't have that for computing. Generally, we don't teach it. I don't think it's by design. I think we haven't developed our understanding of it to the level that a discipline that's been around longer, like electroengineering or electricity, or the electrical charge, and sort of the experiments around it. But I do think we have some aspects that can help us. Specifically, I think things like universal scalability law, Amdahl's law, are very valuable to what we do day in, day out, as engineers in kind of this realm. I also think queuing theory has tremendous value. So learning a little bit of queuing theory goes a long way. And a lot of it is things that we intentionally know, we just don't bring them to the forefront. We all know how to stand in a queue, and we all know some of the basics of queuing. But when you start to look at a little bit more in depth about the math surrounding things like queuing theory, you get a lot more. Category theory. If you're in a realm where category theory matters, like you're doing things like database work, category theory can save tremendous time, and there's entire disciplines that really thrive on category theory. If you're a functional programmer and you don't think about category theory, you're probably doing something wrong. Because there's a lot of things within functional programming, some of the basics that are grounded, and the languages are grounded in more category theory, and I think are incredibly valuable, going forward. So, I think we do have some of the basics, but it's not that something we all agree on. And there's probably things that I'm missing here too. If you're in the domain where you're doing financial modeling, or you're doing anything which is computationally heavy, some of the work that has been done over the years of understanding error in computation, understanding fidelity of models and stuff like that, again, not something that a lot of people are exposed to, but have tremendous benefits. Just understanding that you have a certain, in computation, that you might have an equation that's in math, but understanding that equation, when it's run, has a certain error in it, can lead you into all kinds of different, not sort of compromises, but it can lead you into areas where, well, okay, there's this amount of error, but if I look at the problem a little bit differently, and yeah, I'll change the error a little bit, but in the end, does it really matter? Is it introducing enough error that it's a problem or not? And those kind of things can have dramatic impact on not only that simplicity, but performance. So depending on what you have, it's something to consider, kind of branching out and understanding, in that sort of the why. I kind of hand wove and just kind of gave an example, but the why matters an awful lot, and understanding. So one thing I always, have tried to do is every year I try to sort of branch out into some other area that has kind of, that I need to understand a little bit more. We have to be curious. We have to be inquisitive. We have to look at a lot of the things that are there and kind of question them, so that we can understand and we can branch out ourselves, and kind of bring a lot of those kind of understanding back to our discipline and to the projects we work on. Anyone have a last minute question?
Okay, Todd, I guess that brings us to the end of our time. Thank you very much. This was very interesting. Appreciate it. Take care of yourself.
Thank you. And I will be around in the chat here for probably another 45 minutes to an hour.
Okay, great. Thank you.
Thank you.